All right, hello. Welcome to Chapter 5. Chapter 5 is all about light. Technically, we refer to all of this stuff as electromagnetic radiation. And, in astronomy, we have this challenge in that the things that we're interested in are not readily available to us. For example, if you are a chemist, you go into a lab and there's a bunch of chemicals there. And you can do your experiments and any kind of work you can do just in that room. If you're a biologist, I'll give you an example. A friend of mine who works with scorpions, he goes out to the desert, gathers some sample of scorpions, comes back to the lab, and does his research with the scorpions. He's able to stay in the Antelope Valley to do all that work. Astronomy, we don't have that luxury. The vast majority of things that we care about are extremely far away from us. We don't have the ability to go there. So if we want to study these objects, we are basically dependent on what they give us. And 99.9% of the information that we get from stars and galaxies come in the form of electromagnetic radiation, which I will just commonly refer to as light or photons, depending on the context. There's a lot of different types of electromagnetic radiation. Of course, you're familiar with the visible or optical spectrum, because that's what your eyes can detect. But there's a lot of other types: gamma rays, X-rays, ultraviolet, which we'll abbreviate UV. We have, of course, the visible optical part, infrared, which we'll abbreviate IR. There are microwaves and radio waves. So in this class, we're going to distinguish between 7 different types of electromagnetic radiation. And, there's a lot of information that you get out of light. So this chapter is devoted to understanding as much as we can about light, since it is the way that we are going to learn about these stars and galaxies. So let's look at that. To tell between the different types of light, we have this characteristic length called wavelength that we use. This refers to the wave properties of light. I don't want you to think that light somehow actually has a length to it. It has wave properties as if it has this particular wavelength. So basically, you can kind of consider this a name. The name of light, if I attach to it a certain wavelength to it. Now, the wavelengths that we use are in nanometers, which is a billionth of a meter. And for the light that the human eye can detect, that is roughly between 400 and 700 nanometers. And that's going to be our reference. We're going to reference all types of light to visible light, since we are the most familiar with visible light. At the 400 nanometer end, we call it the blue end of the spectrum, even though if you imagine the rainbow of colors, it's kind of more purplish there, but we refer to it as the blue end. And 700 nanometers is what we refer to as the red end of the spectrum. And these wavelengths here do correlate directly to color. So when we talk about pure red light, we are talking about light that is in around 650 to 700 nanometers. Bluish light's around 550 and so on. So when we talk about the different types of wavelengths, we are referring specifically to the different types of colors of light that we see. What's being shown here is a very kind of crude way to disperse light. Light that we get, say, for example, from the sun is a rainbow of colors, but it's all blended together and it appears white. But if you're able to disperse that light, and they're showing the process of refraction here, passing it through a prism, then we can actually dissect that light and investigate its individual wavelengths. On the left-hand side here is the blue end. But if you go beyond this, which the eye can't see, there would be ultraviolet wavelengths here. So you'd have to use a special kind of camera to detect that stuff. Same thing on the right. If we could see beyond here, we would see infrared wavelengths. So we can also characterize light by another wave property called frequency, although in this class we don't typically refer to frequency very much. It's easier to talk about wavelengths. But there is a relationship between the wavelength and the frequency of the light, and that is when you multiply those two quantities together, you always get the same number, which happens to be in units of speed. And the number that you get is 300,000 kilometers per second, which is the speed of light. And that's one thing that is common to all forms of light, is that regardless of the type, they always travel through space at the exact same speed, which is seemingly an easy thing to remember, except when we look at light in different contexts, it may be something that we forget. For example, around the accretion disk of a black hole. So if a black hole is actively sort of swallowing up matter, that matter gets extremely hot and it spews out lots and lots of X-rays. Those X-rays leave the accretion disk and travel through space at 300,000 kilometers per second. It's a very violent phenomenon, falling into a black hole, right? But then we can also look at a cold, dark, diffuse stellar cloud, just part of the interstellar medium. And, that cloud is not very energetic. It's not bright. And it would give out a steady stream of radio waves. So totally different phenomenon, very calm, not violent at all. But those radio waves leave the cloud at 300,000 kilometers per second. So that's one thing that unifies all types of light. So here is the full spectrum here by wavelength. It would obviously be ideal if you could remember all 7 in the correct order. So visible light lies right in the middle of the spectrum. There are 3 that are shorter and 3 that are longer. So the shorter ones going from the smallest wavelength up would be gamma ray, X-ray, ultraviolet. Those are the shorter ones. We have our visual spectrum. The longer ones, infrared, microwaves. And everything on the right here is the radio part of the spectrum. Everything over here is radio. So it would be ideal if you could remember all 7 of these in their order. But at a minimum, you definitely want to remember that the visual wavelengths are in the middle. And the ultraviolet is paired up with blue. And the infrared is paired up with red. So at a minimum, you can remember those 3 because they are the most common things that we'll talk about. So as I mentioned, all of this light has information that we want. The problem is not all of this light is accessible to us. What you see at the bottom here is a graph of wavelength and atmospheric transparency. At the top of the graph here would represent space. So this would be looking at all the forms of light attempting to enter our atmosphere. And then the arrows come down, and if they reach the very bottom, that's the ground. And as you can see, a lot of the arrows don't hit the ground. There are 2 windows in our atmosphere. That's the visual portion of the spectrum and the radio portion of the spectrum. A big chunk of the radio spectrum. What don't we get? Well, we don't get gamma rays and X-rays, which is good because those things are high energy and harmful to us. So it's okay. But if we wanted to see those things, we'd have to either be, well, for gamma rays and X-rays, we really would need to be in space. The arrows that come down here penetrate through some of the atmosphere, but not in any area that we could really assess them in any easy way. So gamma rays and X-rays are pretty much things that need to be done in space. A lot of ultraviolet needs to be done in space, although the thing starts to drop here when you get close to the visual spectrum. Infrared is kind of interesting. There's a little bump here. That represents about 10,000 feet above the ground. And you can actually access quite a bit of the infrared if you are above the first 10,000 feet of atmosphere. A lot of infrared light is absorbed by water vapor. And water vapor is very common close to the ground. But if you get above that, which you can do either by putting a telescope on a mountain, which is, that's how I did my work. I worked out of Mauna Kea. Well, it was the Keck Observatory on Mauna Kea on the Big Island, Hawaii, and I did all my work there. I did infrared astronomy, and I think it's around 13,000 feet up. We were able to see the infrared just fine up there, so I was able to do my work. Actually, here in the Antelope Valley, we have an infrared observatory. It's in the form of a plane. It's called Sophia, and it flies out of the plant, the aerospace plant down here. And it goes up pretty high, like 55,000 feet, and it gets above a lot of the atmosphere where it can observe quite a bit of the infrared. Goes up all night, does its observations, comes down. So, and a huge chunk of the radio can reach the ground. So you don't need to have telescopes in space for that. You've probably seen very large radio dishes, set up in places, and that's because you can get radio stuff from the ground. So, visible light on the ground, great. Radio, yeah. Some things need to be in space. Some things could be upper atmosphere. But we care about all this stuff. Stars generally emit all of this stuff in different amounts. And there's little bits of information that we find in every part of the spectrum, which helps put together a picture of, what the object is like. So this question here, which of the following list of wavelengths is correct in order of increasing wavelength? So that would mean as you go down the list, the wavelengths would be going up. You may want to pause the video here. The answer is A. The answer is A here. Like I said, this is kind of the bare minimum I'd want you to know. I'd prefer you to know all 7 types of light. But if you remember the 3 here, ultraviolet, blue, and red are visible, and infrared in that order, that would be great. That would be great. All right, so there's another property of light that I want to speak to, and that is that sometimes we refer to light as photons. And when we refer to things as photons, we are referencing the particle-like aspects of light. Particles can do things like, they can bounce off things, so you can reflect light off something. That's kind of like a particle. You can throw something against the wall and have it bounce out. But another aspect of being a particle is that it has energy. And every photon has a particular type of energy that is inversely related to its wavelength. So the symbols that you see here, the E refers to the energy of the photon. The symbol here is proportional to, and the 1 over lambda, that is inverse relationship. So we say that the energy of a photon is inversely related or inversely proportional to its wavelength. That means small wavelengths have large energies and vice versa. Okay. This is not quite the same thing as the brightness of light. So intensity of light refers to how bright an object is. And that's more about the quantity of light instead of the actual properties of that light. So you could have a blue photon and a red photon. And we would say they have the same intensity because it's just one photon. The blue has more energy than the red, however. If you include more and more photons, then the intensity increases, but the energy would stay the same. Blue is still more energetic than red. This is going to be a really important detail at the very end of this lecture. There's a question I have for you at the end that requires you to remember this fact. So, remember this fact. All right. Let's talk about that same question here. Same lists, but we want to know what it is in order of increasing energy. So again, as you go down the list, the energy should be going up. Okay, again, you may want to pause the video here to think about it, but the answer is D. D. It's the opposite order from the previous question. Again, because of the inverse relationship. Because of the inverse relationship. So as we go to the right here, the wavelengths go up. As we go to the right here, the energy goes down. Okay? Great. Let's see what we got here. Ooh, look at this picture Oh my goodness. This is great. Well, first let me talk to you a little bit about how great light from stars is. It's, as limited as we are in astronomy, in terms of how we can study things, the information that is given to us by stars and galaxies reveals quite a bit. There's very little we don't directly know by studying the light from these objects. Here's some of the things we do know, and we're going to be investigating over the course of these next few weeks here. By collecting even some of the light from an object, we can determine the total energy output of a star, for example. We can determine the surface temperature of an object by studying its dispersed light. So if we were to spread the light out by wavelengths and investigate what's going on at different wavelengths, we actually can determine surface temperature, which is something we're going to be talking about in the next lecture of Chapter 5. We can determine the size of a star. So I say radius here, and that's because stars are spheres, and the size of a sphere can be defined by its radius. And we don't see the size of a star, just to be clear. Like in this picture here, you see different kind of stars on the perimeter of this nebula, and some stars look larger than other stars, but that's not due to size, that's due to brightness. So we don't really see the size of these stars, but we can infer the size of the star based on the total energy output and the surface temperature of the star. This is something we'll talk about in a later chapter, like chapter, I don't know. After, it's probably like 18 or 19 or something like that, so not for a while. We can determine the type of chemical elements that exist in the object. We can determine a few things about motion. How fast does the object move? How fast does the object spin? And then, but we can determine the distance to a star by taking several pictures over a period of time, watching how the object moves. We can determine how far away a star is. Now, these properties here are among the most important things about stars. So it's good that we can do this stuff because this is very important. Let me go back, though, and talk a bit about this picture here. So this picture is what we would refer to as a spatial image. A spatial image is basically the same thing as what your eye is able to do. Your eye is extraordinary. It has amazing spatial resolution. You can see quite a bit of detail with your eye. It has great spectral resolution, meaning you can distinguish between lots and lots of different colors. At the same time, you can distinguish spatial information. It's got a huge contrast ratio. It can process images very rapidly. As much as we have very advanced technology in all aspects, we haven't really been able to properly replicate exactly what the eye can do, like create an electronic or digital eye that's just as good. It's very challenging to do something like that. So that's kind of amazing. Now, you see a lot of spatial images. And the reason why you see spatial images so much in astronomy is because it's more relatable. This picture here is something you might see if you were in space looking at this object. Now, generally, you wouldn't see these things because the levels of light are extremely low and really couldn't be detected by the eye. Also, the colors that are being captured here are not exactly going to be the same as what your eye can see. In fact, this image is several different filters all put together. There's at least 3 filters I can tell here. You have this orangish stuff, the bluish kind of pink, and then inside here, this whitish light looks like there's about 3 different filters here. So it's kind of like 3 monochrome images in a way, all stacked together, which is not how the eye works. But most of the images we have from space, or most of the information that we get, doesn't come in this form. There's just not a lot of information here, to be honest. I mean, we'll talk about them, and there's things we can do with them, but it's not the primary way in astronomy information is received. Instead, we do spatial images. Now, the picture in the bottom right here is not well, I'll say this. The picture on the bottom right is an image of our sun, but it's not a spatial image. It's a spectral image. So we could just receive the light from the sun, take a picture, and just see this, orangish ball, which may have a sunspot here or there, maybe a little flare or prominence somewhere. But generally speaking, that's not a ton of information. Instead, if we take the light from the sun, as kind of demonstrated crudely here in this picture in the upper right, we could take some of the light from our sun, and disperse it, spread it out by wavelength, and investigate what's happening at individual wavelengths. And that's what this picture is down here. In fact, let me show you this bigger picture here. This is the dispersed light from the sun. Now, the actual spectrum is very long, so they broke it up into these segments and they stacked them vertically. So the top is the red end, obviously, that's around the 700 nanometers, and the bottom is the 400 nanometers. And this is a busy image, huh? This is a lot going on here. And every single dark line that you see here is called an absorption line, and it contains information about our sun. For example, the line that you see up here, the really big dark one up here, the dark absorption line, is due to hydrogen. There's hydrogen in the atmosphere of the sun that absorbs light and at this wavelength. And so the sun appears dark at this particular wavelength here. There's a doublet here. I believe that's calcium. No, sodium. This must be a sodium doublet here. And that means sodium's in the sun. And it's in the atmosphere and it absorbs light. The presence of these lines reveals the kind of chemical elements inside of our sun. Exactly where their positions are can tell us a lot about if the sun is moving, how fast it rotates. There's just a ton of information in this image here. And this is where we get most of our information because it's just so rich with detail. We call this the interaction of light and matter. What happens is light is generated on the surface of the sun, and then as it leaves, it interacts with the atmosphere of the sun, potentially interacts with the space between us and the sun, and then of course it interacts with our own atmosphere. And exactly how those interactions take place reveal a lot about the properties of these things. So passing through the atmosphere of the sun tells us quite a bit of information about our sun. So we got to understand this. And that's what we're going to be doing for the rest of this lecture here, is we really have to understand how light and matter are interacting to produce this picture here. It requires us to know a bit about atoms. So let's do that. So what I'm going to do in order to talk a bit about this interaction of light and matter, we're going to do a little review of atoms. It's going to be a rather simple review. In fact, honestly, this is probably the most basic review of an atom that one could give. Fortunately, you don't have to have any deep understanding of atoms to really get what's happening with the interaction of light and matter. And so hopefully for most of you, this will be a bit of a review from stuff you've done in previous classes. The picture on the right here is the most basic atom you can have, and it's the most abundant atom in the universe. Over 90% of atoms in the universe come in the form of this thing right here, hydrogen. It has a single proton, which is positively charged, that sits in the center of the atom, which we call the nucleus. You can also have neutrons here, which are neutral particles that help stabilize the nucleus. Hydrogen just doesn't happen to have any in this form. Surrounding the nucleus is an electron cloud, which is a region or several regions where the electrons, which are negatively charged particles that are attracted to the proton, can hang out, basically. The electron isn't free to it's attracted to the proton, but it's not free just to jump over and hang out with the proton here. it has to stay out in this electron cloud. And the electron cloud has a lot of structure to it, which we're going to talk about in a moment here. In terms of the mass of atoms, the nucleus is where all the mass is located. The proton is something like over 1,000 times more massive than the electron. So the proton really determines the mass of an atom. But the size of an atom is determined by the electrons and the electron clouds. When objects come in contact with each other, it's because electron clouds are interacting. When you touch objects, your electron clouds in your hand, the electron clouds in the object you're touching are repelling each other. And that's what we mean when we say touch. It's the interaction of these atoms here. So now this picture is not to scale, not even close. The electron cloud is far larger than this. So I have a question for you, and that question is similar to the scaling stuff that we had done previously. So I give you the size of these two things, and we want to figure out how large the electron cloud is actually going to be here. So the idea is this. We're going to take our proton, we're going to scale it up so it's the size of a basketball, which is about 1 foot across. So imagine you have a basketball in your hand. And based on the dimensions that I give you here, the fact that the proton is around 10 to the minus 15 in size, and the electron cloud is around 10 to the minus 10 in size, how far away would you have to place another basketball to represent the electron? So it's a scaling question. You may want to pause the video and think a bit about this. So the answer here is C. Outside Lancaster, but still in California. Now, when you look at these two numbers here, notice that the difference in the order of magnitude is 5. 5 is the difference. 10 to the 5th is 100,000. So the electron cloud is 100,000 times larger than the proton. If the proton is a basketball, which is roughly 1 foot across, then the electron cloud would be 100,000 feet across. And then you'd have to want to think about what would that be in miles. A mile is around 5,200 some odd feet, so tens of miles away. And C is consistent with tens of miles away. In fact, I think if you work out the numbers, it comes out to be around 60 or 70 miles away. So if you're in the Antelope Valley, the electron will be buzzing around. It could be as far away as Bakersfield, Richterville, downtown LA, things like that. Now, the reason why I mention this right now is because under normal circumstances, atoms have electrons, and this space is empty. This enormous space is empty. But occasionally, stars can strip away their electrons. And when they strip away their electrons, you get some really exotic forms of matter, things like neutron stars and black holes. And so this will be an important point later in the class when we get to these topics. So that's why I mention them right now. All right, so let's talk about the nucleus of an atom. The periodic table is organized by protons. The atomic numbers for things correspond to how many protons exist in the nucleus. If you change the number of protons in an atom, you have a totally different atom. And the chemical properties of these atoms are determined by how many protons there are. So hydrogen with 1 proton, that's a particular type of atom, but if you add a proton to it, you get helium. It's an atom with totally different chemical properties to it. Carbon always has 6, and so on. So this is all chemical properties. This is the different types of atoms. It's all determined by protons. Protons are the most important thing for atoms, clearly. Now, the atomic nucleus can also have isotopes. The atomic nucleus can also have neutrons in it. And atoms with different amounts of neutrons in them are called isotopes. That doesn't change the chemical properties of the atom, though, because again, it's determined by the number of protons. So hydrogen normally exists without a neutron. But you could add a neutron to it. It's called deuterium, and that's still hydrogen. It weighs a bit more, slightly larger, but it's still hydrogen, and you could make water with deuterium. In fact, every time you have a sip of water, you are consuming a bit of deuterium. And it's like 1 every 10,000 or so hydrogen atoms is deuterium naturally. So it's not necessarily harmful unless you have a lot of it. In fact, you could make water entirely out of deuterium, and we call that heavy water because it weighs something like 8% more or something like that than regular water. So you actually would feel a physical difference between them. And if you drink it, your body works by chemistry. So if you drink it, your body's like, great, this is water. But it could damage you because the water that you're drinking is actually heavier and larger, and that could have a very adverse effect on your body if your body is not anticipating a larger, more heavier type of water, basically. Carbon, under normal circumstances, has 6 protons, 6 neutrons. We call it carbon-12. 12 is just the sum of the protons and neutrons. Carbon-13 has an extra neutron in it. Still carbon. You can make sugar out of it, just like you make sugar out of carbon-12. Still carbon. Okay. We typically give these mass numbers, 12, 13. These are mass numbers, the sum of the protons and neutrons. And we typically give the name of the atom plus a mass number to distinguish between isotopes. Hydrogen's special for some reason. I don't really know why. We actually give different names to the different isotopes of hydrogen. Tritium is 2 neutrons, which is very unstable, but can exist. So I don't know why we give different names, but I just want to point that out because some students see these 2 names and they think they're different elements, and they're not. So, all right, that's neutrons. That's isotopes, and that pretty much covers the nucleus of the atoms. I really can't give you anything more complicated than that without throwing you some like quantum mechanics or something here, which I won't do. You're welcome. All right, let's talk about the really important stuff, and that's the electrons. The electrons are where the action is taking place here. This slide is very important, very crucial to understand this stuff here. What it says here is the number of electrons in an atom normally matches the number of protons. If you're talking about hydrogen, 1 proton, 1 electron. Helium, 2 protons, 2 electrons. That's normal. We call that a stable atom. If you were to add or remove electrons, those are referred to as ions. But we're not talking about ions. We're talking about regular atoms here. The electrons orbit the nucleus in the electron cloud, but they are restricted to very specific radii and energies. To a large extent, you could kind of compare atoms to our solar system in the sense that the sun is like the nucleus and the planets are like the electrons as they go around. What's different about that is you can have a planet at virtually any distance you want to. That's not true for the electrons. The electrons are restricted to very specific orbits, and they must stay in those particular orbits. So, for hydrogen, it has that 1 electron, and the electron can, to some extent, be in whatever level it wants to. It wants to be as close as possible to the proton because it's attracted to it, so it's going to hang out in level 1 down here, which is what we call the ground state. But it can move to other levels. Now, the structure of these levels are determined by how many protons there are, and therefore they're unique to each atom. Hydrogen has a structure to it. Helium has a different structure to it. Every atom has a different structure, a different set of levels where the electron can hang out. It wants to hang out on the bottom if it could, but it can move to other levels. if it is given the ability to do so. All right, so I have a question for you here. We talk about different energy levels, which correspond to different distances. Now, realizing the fact that the electron would like to stay as close as possible to the proton, we can speak of these levels as having different energies to them. So think about this question here. What is the correct relationship for the energies of electron that occupy these different levels? Think about this for a moment. You may want to pause the video and think a bit. But I'll tell you right here, the answer is B. B. The ground state is the lowest energy. As you go up, the energy increases and increases. The best way to think about this is imagine something else that has an attraction, right? Gravity. If you think about taking an object, holding it above the ground and letting it go, it falls, right? It's attracted to the earth. It wants to be down if it can be down. If you want to move an object further away from something it's attracted to, you have to lift it. And that requires energy to do that. And that's why as you push the electron farther and farther away, it's going to have more and more energy because you're putting energy into allowing the electron to be farther and farther away. So you should really think about this as kind of like a gravitational field. The nucleus is the ground. And as you get farther and farther up, it's harder and harder to get there because it takes energy to do it. All right, great. Let's see here. Oh my goodness, look at this. A lot going on here. All right, here it is. The interaction of light and matter, right here. Photon absorption. The question now is, how do we get those electrons to those higher levels? How do they get the energy to do this? Well, we established earlier in this lecture, photons have energy. And so photons can impart the energy to these electrons. When the right kind of photon passes by the electron, it can be absorbed by the electron, which the electron absorbs that in the form of energy, and then it can kick to a higher level if it has the right energy to do that. And that's how you move electrons to these levels. They absorb photons, but not any kind of photon, certain photons. You should think about this in terms of like walking up a flight of stairs. Okay, walking up a flight of stairs requires you to make very precise steps. If you don't take a step that's high enough, you're not going to reach the next level. If you take a step that's too high, you have to lower your foot to the correct level. So every time you take a step, your foot needs to go to the exact right level to make it up to the next step. Same thing with the electrons. The photons that it absorbs have to correspond to exactly the right amount of energy between the two levels. If a photon doesn't have enough energy, it won't interact with the electron. If it has too much energy, it's not like the electron could take some of it and leave some behind. That doesn't happen. It has to have the exact right amount of energy to make that jump. When I showed you that picture of the sun a little while ago, all those dark lines were absorption lines. Those were atoms that had photons pass by them, and some of those photons were absorbed. The photons are missing, and that's why the lines appear dark, because there's very little light, if any, at those wavelengths. This is one of the ways that light and matter interacts through the photon absorption and emission. I'll talk about emission a little bit here. Right, so let's think a little bit more about these photons, though. All right, in this picture here, we have different transitions. We can go from level 1 to 2, 3, or 4. I even put down here a transition that would be from 3 to 4. If you think about the step analogy, right, what's the biggest step? Think you have step 1, 2, 3, 4, and look at the physical gaps here. The physical gaps here do correspond to how big of a step you have to take. So thinking about what's the biggest step here, right? Think about that for a minute. The answer is C. The biggest physical gap is 1 to 4. It's the biggest step, therefore it requires the most amount of energy. All right. The next biggest looks like it probably would be, kind of hard to tell here, maybe 1 to 3, because I'm looking at 3 to 4. It looks maybe a little bit shorter than 1 to 3. The shortest is definitely 1 to 2. That's the littlest. That's the least amount of energy. Littlest. Is that a word? I don't think it's a word. All right. Okay, now, this is it. This is the question. This is the climax of this lecture. It all leads up to this. This is a really important point regarding this absorption stuff. Now, we're going to imagine we have an electron down here in level 1. And it can either jump to level 2 or it can jump to level 3, just for the purposes of this example here. And there would be photons with a particular wavelength that could take you from 1 to 2 or from 1 to 3. What I want you to think about here is what would be the correct relationship for the photons that can do these two things. We just established that it takes more energy to go from 1 to 3. There's less energy from 1 to 2. So what do you think about those wavelengths there? Think really hard about this one. This is very crucial. Okay, ready? The answer here is A. A. The photon that needs to go from 1 to 3 is a shorter wavelength. Why? Because we established earlier in the lecture that there's an inverse relationship between the energy of a photon and its wavelength. The more energy you need, the shorter the wavelength will be. 1 to 2 is not as big of a step, so the wavelength will be larger for that one. Okay? The wavelength, for example, if I had to talk about the wavelength from 1 to 4, that would be even shorter. That would be even shorter. Okay. Let's talk about emission now. So, these photons get absorbed. The electrons jump to higher levels. What next? Well, they eventually have to fall back down. And most times, that is a spontaneous process. In fact, it's one of the few processes in nature that we think, at least at the moment, is purely random. Now, once an electron gets kicked to a higher level, it comes back down pretty quickly, like nanoseconds or something. But exactly when a particular electron will do that is not precisely known. We have sort of an average that occurs. But when it does come down, it has to release photons. It has to give up energy to go back down to lower levels. And we call this process emission. It's the complete opposite. If you go up, it's absorption. If you go down, it's emission. And this picture shows us what hydrogen is like. And this is all showing us wavelengths going down. But guess what? If you go up, it's the same wavelengths. In fact, this set of wavelengths here is special to hydrogen. This set is a pattern of lines that only hydrogen has because of its unique structure. Most of these lines we can't see, by the way. The only ones we can really see are these three right here that are transitions from 2 to higher levels. 656.3 is red light. 486.1 is like bluish green. And 434 is very deep blue. You kind of can see the 410, although the eye really doesn't work so well past 420. Around 410, it's very difficult to distinguish that because your eye just is not responsive there. Now, when an electron gets kicked to a higher level, so I mentioned that photon from 1 to 3, right? The photon from 1 to 3 is this 102.6 number. The photon from 1 to 2 is 121.5. So bigger wavelength, less energy. Now let's just say the electron gets kicked to level 3 from level 1. It's 102.6 nanometers. How exactly does it go back down? Well, I mentioned it's spontaneous, that's true. But what's also spontaneous is how it goes down. Does it have to go back down to 1? No. It goes back down to any allowable state. So being at level 3, it can go to 2 or it can go to 1. If it goes to 2, it will first emit the 650 6.3 nanometer photon. Then it can emit the 121.5 and get back down to level 1. Or it could just emit the photon that it absorbed originally and go right back down to 1. These photons, by the way, they're not like stored. It's not like the electron like keeps it and then gives it back later. It's energy that's taken and turned into motion, basically. And when it releases it, these are all the allowable things that can be released. So it doesn't have to go down the same way it comes up. But when we witness this pattern of lines, we know we're dealing with hydrogen. I could show you this same picture for any element. And we can see what the pattern of lines look like. And for every single star, there is a very complex pattern of lines. That's that picture I showed you before with all the absorption lines, all the dark lines. There are thousands of lines there. And you have a lot of overlapping patterns of different elements. There's sodium there. There's calcium. There's hydrogen. There's helium. There's all sorts of elements in there. And if you know all of those patterns, you can determine what type of elements exist there. And in fact, you can determine what amounts they're there as well. So that is one way we're going to talk about light and matter interacting. In the next lecture, we're going to get to a second way that you can get this thing done.